Well, welcome to the Institution of Civil Engineers. For those of you that don't know me, I'm Steve Featherstone, formerly of Network Rail, now working as an independent advisor, and one of the clients that I work with is Geobear Global. It's lovely when you leave Network Rail. You can work with people that you really like, that do things you really respect. When you work in Network Rail, sometimes you have to work with people that you don't like, but you don't have to do that when you're in the outside world. So I really like working with Geobear. There's a lot of solutions that you're going to see, and I look back to when I was National Maintenance Director and Track Director and think, God, I wish I'd known that then. So hopefully, over the course of the next hour and a quarter or so, you're going to see some solutions that you think, yeah, that's going to be great. And it's just, go away, put it in the menu of options that you've got, and maybe one day you'll think, I'll give Geobear a call. What these guys have done, they've turned the art of geopolymer injection into a science. The design capability, the science and the knowledge that now sits behind it is fantastic. Now, one of the reasons I'm also hosting this is that I was a past president of the Permanent Way Institution, and just to say thank you to the Permanent Way Institution team at the back for helping us with the organisation, the logistics, all of your badges that you are wearing, and making everything work so slickly. So thank you very much to the team at the back for getting us to the starting line. And we got three speakers today: Pete Luby, then Andy Lee, then Mohammed Webby, and they're going to take you through what Geobear have done and how we've successfully stabilised the famous embankment slip on the Severn Valley Rail. I've given away the secret now that it's worked, but hopefully they'll tell you that over the next few minutes. And so first of all, I will hand over to Pete Luby. Those of you that work in Network Rail will recognise Pete, as he used to be one of the senior directors in Network Rail.
This one? Yep. Thank you, Steve, and thank you to the PWI for helping us get this event together. Thank you to you all coming out on a particularly soggy day in London, so I really appreciate the effort and really hope you get something out of today. So today I'm going to give you an update, an introduction to Geobear very quickly. We're going to give you a better understanding of geopolymer materials, how they're used in the principles of injections. Then we're going to talk about the Severn Valley Railway trial, which we're really pleased to show you. And then we'll take you through a number of case studies and other applications that you can use our solutions for. And then afterwards, you have the opportunity to grill us in the Q&A. Okay, so Geobear, we're a global leader in non-disruptive solutions for foundation and infrastructure settlement and subsidence problems. And that non-disruptive part is the really key part of our operation, that we can come into areas pretty quick and solve some pretty difficult problems, as we've demonstrated, and you'll see through some of the examples we'll show later on. The company was established in 1983 in Finland, originally under the Eurotech name, until 2017, where it transformed into the Geobear brand, as you see today. The UK business was established in 1989, and we currently have offices in Wolverhampton, Winchester and Sandy, and we also have an operational base in Dublin, so we've got quite a lot of work in Ireland and Northern Ireland at the moment. What we're really proud of is, and you'll see a lot of it today, is our in-house design team, for engineering and designing solutions and solving problems for our customers. And that innovative, different way of looking at problems is really, really what you'll see again today, but also what we're really proud of. We also work a lot with third-party consultants and also material testing labs to ensure that all of our products are fully tested, certified, etc. And we do a lot of external support and draw a lot of external support into our operation. And to date, we're over 200,000 successful projects for the solutions that have been developed. So a worldwide team. Talk to you about the UK and Ireland. We have a base in Sweden, Finland and Poland, but we've also reached out to the USA and sunny California, and also we have a team in China. We work across multiple sectors, a lot of work in residential, which is the bulk of our initial work, where we do a lot of private work for individuals who have subsidence problems with their houses, but also through a big bulk of insurance companies. So we work with a lot of big insurers. But from a commercial and infrastructure point of view, we work with all of the major players out there. Airports, we've done a lot of work at Heathrow, Gatwick, Glasgow, Bristol, all the main hubs we've worked and done stabilisation projects for. A lot of work on highways, motorways, A roads, ports. We do a couple of jobs for the Ports Authority and lots of work for utilities and in particular water companies who we pick up quite a lot of work from. And from a railway point of view, we work directly for Network Rail, but also for a lot of Tier 1 contractors for Network Rail. So our purpose as Geobear is we enhance people's lives and make the planet's future by bringing safety and stability for all. Our vision is to be the leading provider of sustainable, data-driven asset management solutions in the built environment. And really what I hope you see today is our values, our SPIRE values: safety, partnership, integrity, respect and excellence. It's our internal, but also how we try and portray ourselves externally as well. So that's enough of me. I'm going to hand you over to Andy, who's going to give you an introduction into geopolymer.
So I think it's quite important to explain to you what geopolymers are and really how they work before we get into the nitty-gritty on the Severn Valley Railway. So what are expansive geopolymers? They are two-component geopolymer comprising of a resin and a hardener. And when you mix them together, there's a chemical reaction, and that leads to a state change from liquid to solid. And there's a consequential volumetric increase due to that chemical reaction. There's a short clip here I'm going to show you of us injecting a mixed liquid polymer into a void, and you can see the reaction as it moves forward. So the liquid's going in. After a few seconds, the chemical reaction will start. And it's finished. So this polymer is a void-filled polymer, and so it's characterised by a fast chemical reaction, and it's low-density, high-volume, expansive geopolymer. We have a range of different polymers which have a different reaction profile, and we select the geopolymer for the problem that we're facing. Yeah, we can put around, there's two polymers here. One is a lightweight void-filled polymer. Another one is a high-strength ground reinforcement polymer. So they're two different polymers, and they've got quite different densities, although they're comprised of essentially the same material. Now, depending on the geopolymer type, the geopolymers can expand up to 40 times their original volume and generate different lifting pressures. And what you saw in the video clip was a high expansive volume, and that was probably up to 40-fold volume expansion. But the amount that a polymer will actually expand is controlled by the confining pressure at the point at which you inject it. And so there's a relationship between the confining pressure and the amount of expansion you get. And understanding that relationship is really important if you want to design with geopolymers. So how strong is geopolymer? The strength is a function of the density. So as the density of the polymer increases, the compressive and the compressive strength and the tensile strength both increase. And the two examples you've got out there, One is a low-density polymer, and one is a high-density polymer. They will both have different compressive strengths as a function of that density. It's quite important. What is also interesting to note is the compressive strength and the tensile strength are fairly similar at the same density, so it's not like a concrete which is strong in compression and weak in tension. These are strong in both directions, if you will. And we test these material properties in the lab, so we know what the physical properties of the material is for any given density, and you can work out the relationship between density and strength. It's very important. You would expect the stiffness to go up as the density increases, so it's sort of proportional to the compressive strength, but the stiffness modulus increases proportionate with the density. So another thing with geopolymers is their ability to resist cyclical damage. So the polymers have been tested to see what settlement you get under cyclical loading. And what we've found is that the performance of geopolymers at different densities will generally outperform normal, typical engineered fill, type 1, compacted fill. If you inject geopolymer into those materials, you'll find that their resistance to cyclical damage is greatly increased. So, other key properties. Unlike conventional grout, geopolymers have a hardening time typically of less than a minute. So you saw the reaction there went from liquid to solid in a matter of seconds. And the full strength of geopolymer is normally achieved within 24 hours, and probably 90% of the strength in a matter of 1 hour. So they rapidly harden, which is quite different to conventional grouts. Cement-based PFA grouts do take quite a length of time to get to their compressive strength. And so that's an advantage with geopolymers, in that we can do our treatment and get a result very quickly, and that saves time, and time is important in terms of completing projects quickly. The geopolymers do not require water to initiate the curing process, so when you've got a cement-based PFA grout, you generally add water. There's no water added. We bring to site two liquids, one's the resin and one is the hardener, and they are mixed at the point of injection under pressure and injected straight into the ground. There's no added water put into that process. The other thing to note about geopolymers, the samples are being passed around, you'll notice they're very light. The actual density is less than 1,000 kilograms per metre cube, so much less dense than water in most cases. And so they're very light materials, lightweight materials, and that's due to the cellular structure, because essentially geopolymers are basically polyurethane-based chemistry. That's what it's based on. And you can see the the cylindrical bubbles here. Inside the bubbles there's trapped carbon dioxide. Into carbon dioxide that leads to expansion when you mix the two chemicals together. So they are lightweight, strong materials, very flexible. We've had them tested extensively, because it's very important that if you're injecting chemicals into the ground, you're not going to contaminate groundwater or generate a leachate problem. And so we've had the materials tested. We've crushed the material up into fine sand-sized particles and done leachate testing, and we've not detected any harmful chemicals above laboratory detection limits in the leachate. So we're very confident that they're safe to use over aquifers, and we've never had a problem reported in their use in terms of the impact on the environment. So they're sort of environmentally friendly sort of products. The other thing to consider is a carbon footprint, and because when you compare the use of geopolymers to traditional cement-based grouts, essentially we use a lot less material to achieve the same end result. And that generally means that the carbon footprint of a geopolymer-based solutions are lower than conventional solutions. And we've had this independently verified by Carbon Footprint Limited, who've done some carbon study analysis on our projects to compare the way we would do a project against a conventional treatment. And we're looking at round about 46% less carbon emitted on typical rail-based infrastructure projects. It varies from different types of projects, but for rail-based solutions, it's roughly half of the carbon emitted, so that's a good positive thing for geopolymers, in my opinion. So let's look at a few improvement principles. So, I mean, the way you design with geopolymers is essentially there's two basic types of soil, as we probably know. There's granular soil and there's cohesive soil. So clays and silts and sands and gravels. And the way in which the geopolymer works is different depending on what type of soil you've got. So it's sort of important to know what you're dealing with. Dealing with sands or you're dealing with clays. It's quite important. So at the point of injection, so when we do our treatment, we drill a hole, small hole, 15, 16 millimetre hole. We put into the ground an injection tube, and we inject through that tube the polymer under pressure. And when you have a granular soil, like a gravel, the initial permeation is through the intergranular pore space. So you're flooding the pore space in between the particles, and that's called permeation. When you're dealing with a firm or stiff clay, and this is typically when we're looking at clay shrinkage solutions, where we have a desiccated fissured clay, the polymer will migrate along the fissures, along the void, and through the voids, not through the clay itself, not through a stiff clay. So that means there's less what I call hydraulic fracturing. But if you have a very soft clay, and soft clays is what we had at the Severn Valley Railway, if you inject geopolymer under pressure into a soft clay, you will hydraulically fracture it. You'll create fractures, and into those fractures the geopolymer will flow and then expand and harden. And you sort of reinforce the clay soil through these fractures. And that's shown on this picture. So, where's my pointer? Here we go. So these are the vertical and horizontal fractures of geopolymer within a clay matrix. And they typically form a pattern, cross pattern, of interlocking fractures. And if you consider this maybe a very soft clay, 10, 15 kPa, and inside it you put a geopolymer, it could be 1,000 kPa in terms of its compressive strength. So it's rather like putting in steel into concrete. It's reinforcing the soil. So that's essentially how it works. We fracture the clay, we fill the fractures with the polymer. The polymer is very strong, so you get a composite effect of strengthening the clay. Here's some pictures from an excavation we did. This was actually done in a stiff clay, and it just showed how the polymer migrated along an open fracture. And we dug it out of the ground. It looks like this. That's an actual slab of polymer that's the same shape as the fracture it migrated along. So that's some fractures. So let me talk about equilibrium pressure, the science lesson, bit of this. So key thing is to know about polymers is that the way they expand under pressure, and so the swelling pressure increases. The swelling pressure increases as the volumetric expansion gets smaller. So essentially, when you have a very, very large expanded volume, the pressure is very low. And conversely, when you have a small volume when there's high pressure, this is in the expansion phase of the geopolymer. That's represented in the blue expansion on this graph, on this picture, not graph. And so essentially, at atmospheric pressure, the polymer has its maximum volume, which is called free rise density. So if you were to inject the geopolymer on the ground here, it would expand. The only thing that's stopping expansion is the weight of the atmosphere on top of that polymer. So that's the expansion of the actual geopolymer's free rise density. This is a key thing to know. Now, when you inject in the soil is working against that expansion force, and that's represented by the red arrows. So you have like a battle between the expanding polymer and the confining soil. So there's two basic forces opposing. And the point at which the polymer will stop expanding and harden is at this point here. where the sort of expansive force of the polymer is matched by the confining pressure of the soil. This is a key design point that we need to know this in order to design polymer solutions. You need to solve for that point, which is called the equilibrium pressure. And once you know the equilibrium pressure, you can define what the properties of the polymer is in the ground. You can predict the compressive strength in the ground by knowing what the equilibrium pressure is. And myself and Mohammed have developed a series of spreadsheets that do these calculations based on the theory developed by a guy called Manacero, who's an Italian professor who did most of the work in geopolymers. Let me just come back to this. So how do we know it works? Here's an example from a job we did in Middlesbrough. It was on a water treatment facility, very soft clay. The blue line was in situ shear strength. We were required to at least double it to meet the specification. And the red line is after treatment. And we did a model that predicted what the performance would be, and that's shown by the black dots. So our actual performance closely matches our model. So this is how we sort of model what we think is going to happen. And that would include how many kilos, what depth, what spacing, which polymer. That's our design. And so it's been proved in the field on many occasions that we're pretty good now at calculating exactly what we need to do. This is not a guesstimate, it's not an estimate, it's an actual calculation. So that's quite different to how this has been done in the past. Now, if I just talk briefly about loose granular soil, here we have an example of the permeation. So this was done down in the south of England, a place called Hurst Castle. We did a trial on the beach where we excavated a trench. It was full of beach shingle, loose gravel, and we injected into that gravel to see what would happen. And the polymer forms things we call bulbs. So it's a big lump of gravel and polymer mixed together because the polymer is actually in between the gravel. It's a bit like concrete. When you cut this stuff open, you can see like polymer and then gravel all mixed together. So you get these large bulbs forming, and the size of the bulb is proportionate to how much you put in and the depth at which you inject it at. Here's a smaller lab bulb done in one of these test cylinders using sand, a finer grain material. But essentially the same thing is happening. The polymer's permeating through the pore space and then it expands and forms this bulb. And it's that expansion that causes compaction. So in granular soil, we increase bearing capacity through compaction, not by creating fractures, quite different. And so the densification of the soil can be estimated from the volumetric expansion of what these bulbs. So if we can predict how big the bulb is going to be for the amount of kilos you're going to put in, and based on that we can work out how much the density of the soil is going to increase. That means how much the angle of friction is going to increase, and then how much the bearing capacity is going to increase. And we have modelling tools that will calculate that improvement. Final example, this is from a project in Glasgow. And the red, this is in loose sand. You can see on the line here from 10 SPT down to about 5. So pretty loose sand. We injected at about 3 or 4 levels, and we did a post-treatment SPT test. That's measured in the blue line. So we got a consistent improvement, which is very close to our model prediction for granular soil. And that's sort of explaining to you how it works in clays and how it works in granular material. So the next bit is to actually talk about the SVR trial, but I think it was important to try and give you a little bit of an understanding of how this might work in the soil, because you have to think about in the soil, what's happening in the soil is very important. So as was mentioned, last year we did we were asked by Severn Valley Railway to assist them in stabilising a section of an embankment that had some problems, some slope stability problems. In fact, long-standing issues on this particular slope. And it's in a place called Alverley Wood in Shropshire. right next to the Severn Valley, and this is a heritage railway, as you probably know. You can see from the picture the track was showing signs of distress, which resulted in a 300mm deviation from the design geometry. And that meant they had to put a severe speed restriction on the line, 10 miles per hour. And the amount of deformation was about an 80-metre section parallel to the River Severn that was showing instability. And so we were asked to look at this to help them stabilise parts of it using our technology. And if I just show you the cross-section, this is the actual, quite a steep slope. This is the actual river valley. This is like a drainage ditch, and then this here is the actual embankment. And they put the railway on the top, and the River Severn is here. Groundwater flowing down here, through the embankment into the river. So this embankment is not very big. I think that's why would such a small embankment have a problem? Because it's not a very high embankment. We're talking 4 to 5 metres maximum height. Other parts it's only a metre or so, not a very big embankment. But nonetheless, it's been shown historic movement. The reason becomes clear when you drill boreholes into it. Let's look at the track tilt sensors. Here's some tilt information on the actual track itself. These are the sensors. We chose this location for the trial because we had some good data. We got some tilt data beforehand, so we can see what improvement we got afterwards. And there was data available, in 3 sections. They had some data, and the section that we chose to treat was 17684, which is shown by the red line. So that's the tilt information for the section that we were asked to trial, essentially the worst part of the embankment. Ground model. So we were given a site investigation executed by a different company, Ground Investigation Piling, who are from Dudley. And this shows you the general geology of the actual embankment, which is on the top here. This is your embankment fill. This is loose ash fill. We have a water table here. And then you have, these are carboniferous deposits, hail zone formation. So they're weathered coal measures, essentially. But when you look at this geology in detail, there's one thing that catches the eye, and it's in this section here, where it says there's presence of occasional thin coal and occasional very soft, highly plastic shear surfaces up to 10 centimetres thick. So plastic shear surfaces. So why would that's suggesting there's some very soft zones inside this weathered mudstone, because weathered mudstone is normally pretty stiff clay. So we have stiff clay, then very soft clay, then stiff clay again. So this was interpreted by the ground investigation contractor as probably the result of an ancient landslide. So this landslide probably occurred at the end of the last ice age, and so it generated a shear plane inside the top of the weathered mudstone, and this is at a depth. This shear zone is about 4 or 5 metres below ground level. Now, obviously, when they built the railway, they didn't know there was a shear zone there. This obviously been there for thousands of years, and so they stuck the embankment on top of the shear zone, and then built the railway on top. And so when GIP did some slope stability analysis of this embankment, it was shown that the minimum factor of safety occurred on when you have a shear surface through that shear zone. So essentially, all of this hill is sliding into the river along that weakened shear plane. So we have a plane of very, very weak clay or soft clay, and the weight of the embankment is such it's just slowly sliding down into the river. So this is essentially the analysis that the GIP did, which was indicating what the problem was. So it was a slope stability problem. And in order to make the slope model work, you have to assume that the shear zone is at what we call residual shear strength. I mean, very, very low shear strength, no effective cohesion, low angle of friction. Now, the original proposal was to soil nail through the shear zone into Compton bedrock. So the idea was to sort of drive soil nails through this direction into the Compton rock to try and reinforce across the shear zone. So that was the basic original solution. And so it was Geobear's task to think, well, what else could you do with this sort of a problem? And I'll lead that onto the design. I'm going to hand over to Mohammed, who will take you through the design side of it.
Thank you very much, Thank you very much, Andy. Now into the design part of the presentation, or on the SVR. So one of the key parameters that we needed to understand is how do you apply the treatment, where do you apply it, and to which extent that you want to apply the treatment to. So the first step for us to understand this is to come up with our own model. So what we've done, we've taken all the ground information that Andy kindly described and built a Plaxis FE model. And that would basically allow us to understand, or better understand, what sort of factor of safety that the embankment currently have, and also understand where do we need to apply the treatment in the most optimum manner, okay? So we created this model, as you can see it here, and we basically built up the model based on the data. So you can see the ash fill in the dark green, and then you've got the weathered clay, and then you've got the slip surface, followed by, again, clay, and so on. So we created this model, ran it, and basically quantified the factor of safety and understood how the embankment is actually slipping. So based on the analysis that we've carried out, we've estimated that the factor of safety is somewhere between 0.8 to 0.9. And we basically verified based on this, we verified the geotechnical parameters that we had for the model, that we inputted into the model. And then we studied what's the amount of cohesion that we need to add, or extra strength that we basically need to add to the embankment to basically get it to some sort of a level of stability. And we've estimated that we need to improve the cohesion of the shear zone from 0 all the way to 10 kPa. So that was the sort of main design parameter for us. That was the ultimate design parameter. So, and in order for us to do that, we've estimated that if we manage to improve the shear strength, the undrained shear strength of the plastic clay or the shear zone to 100 kPa, we will be able to achieve that increase in the cohesion of 10 kPa. So that's the sort of design philosophy that we followed. So we ran the model, and we also managed to quantify what's the optimum treatment zone that we need to apply across the embankment. And we found out that if you actually apply the treatment within the red dashed area here, this will give you the most cost beneficial treatment. So, one way of doing this is to simply apply the injections everywhere, flood the entire embankment with the geopolymer material. But obviously this will be expensive and will be time consuming. So by this analysis, we were able to narrow down where we need to apply the treatment. And we've understood that this is the most effective area to apply the treatment to, and will give you the most benefits. So, based on all this analysis information, we basically carried out a detailed design, and we came up with this design. Some of you have attended the trials and live and seen this going into the ground live. So what we've done, we've treated out of that 80-meter distressed section of the embankment, we've selected 10 meters within that 80 meters, and we basically installed the injections, every alternative sleeper bay, as you can see here, and we spaced them at roughly about a meter apart from each other. So every alternate sleeper bay, and then we extended the treatment outward, away from the track, towards the river. And we've carried out the injections at different levels. So under the track, we treated basically the ash, and then as we were stepping away, we were increasing the amount of injection intensity, and we've used a high density geopolymer to basically treat the shear surface and inject through the shear surface, as you can hear, with different materials and different injection dosage. So this was the design that we came up with, and the sensors, the tilt sensors that Andy described earlier, are actually located almost right in the middle of the test section. Okay. So we've developed the design, and last year on the 26th and 25th of July, we actually carried out the installation, and we've used our mobile injection unit. So our mobile injection unit is an injection unit that is mounted on a wagon that is connected to a train, to an engineering train, and basically it has all the equipment in-house within the unit. So everything we need is within that unit, and the injection hoses are extended from that injection unit to the injection area. So our hoses can extend almost up to 120 meters away from the injection unit. So your injection unit can sit 120 meters away, and the hoses can just come up and inject. You can see here the injection tubes already been installed. So these are 12 millimeter diameter tubes, and they're installed to the design depth. And basically we go to every single tube and connect the injection gun and start the injection. We've installed approximately 136 injection tubes, and we've pumped roughly about 2.5 tons of material within that section. During the injections, we've monitored track heave, so we had laser level monitoring at different locations, monitoring if there's any movements that's being experienced on the track. And following the completion of the injections, we've carried out dynamic probing. So before we started, we did dynamic probing, and after we finished, we also carry out dynamic probing just to have a comparison of what happened instantly between before and after the injections. We managed to complete the work in 2 10-hour shifts between those 2 days, and after that, so we've got the probing, then we started looking at the tilt and inclinometer data for a period of roughly about 6 months to see what's the long-term impact. So the probing data gave us an idea of what happened on the short term right away after we finished the injections, and the tilt and the inclinometer data gave us the long-term picture of what has happened. Performance. As I mentioned earlier, we've carried out dynamic probing. So dynamic probing, as you can see here, my colleague Steve is doing the probing, and I'm standing here watching and trying to participate in heart. So we've taken the dynamic probing data and converted it into shear strength. Now, and we've done the probing in 2 locations. So 1 pre-injections and 2 locations after the injections. So the red curve represents the shear strength across the depth from the probing before the treatment. So that's the red line, okay? Now, the blue and the green lines represents the dynamic probing results following the injections at 2 different locations, and the black dashed line is the average line between them. So if you compare what happened within the shear zone, the shear strength was around 25 kPa, and we've managed to improve that all the way to around 120 kPa. As you can see here, there's a significant jump in the shear zone, and because we specifically targeted that area surgically. And you can also see, because we've also done some injections within the mudstone on top of it, or the weathered mudstone, you can see also a significant improvement in the shear strength of that as well. So it's not just, yes, it's already strong, but it's also been improved from about 100 kPa to about 160 kPa. So a significant improvement in terms of the shear strength. So that's the short-term picture, what happened right after we finished the work. So this was done literally after we finished the injections. Now, based on the information that we've obtained from the shear strength, we said, okay, we need to verify, okay, are our initial assumptions with the modeling are correct or not? So we've taken all that data from the probing, we've plugged it into the model, and obviously we've used some of our in-house design models that quantifies the improvements that Andy kindly described earlier, and we've quantified what sort of level of improvement that each material or each layer would exhibit. So what happened to the ash, what happened to the head, and what happened to the shear zone. So, and these are the highlighted parameters. The highlighted parameters are the parameters that actually been affected by the improvement, and that was quantified from the probing data. So we've taken that and we've carried out the analysis. And based on the analysis, we've estimated that if this works, it should improve the factor of safety push it from 0.8 all the way to around 1.2. So a significant improvement in the model and the factor of safety. Now remember, we were not working to a very specific, a rigid specification, so we were not given a specific target, but this was done as a trial to understand, is this technology capable of improving the factor of safety and improving the long-term stability? So the modeling backs up the theory that this should improve the overall stability. So what we've done, we've examined the data from the tilt sensors. So and we focused on the middle part. Obviously, this is where we've done the treatment, and we focused on that. And what we've done, we've looked at 2 years worth of data, and also, so we looked at what happened in the last 6 months, but we also had to look at what happened before, because we needed a comparison, and we needed to make sure that we do the comparison in a way that they're comparable, where the weather is roughly the same. So we don't want to compare a summer measurements with winter measurements, because that doesn't make sense, because water is a big factor in all of this. So we needed to make sure that our comparisons are happening within similar seasons, and they're not very, very different. So we've taken all that data and pre-processed it, and we also made sure that we had to normalize the data for the starting tilt values, because it doesn't make sense to compare data that has different starting tilt values on the track. The behavior will be completely different, so we had to normalize for that. So based on this, we managed to generate these graphs from the data, the processed graphs, and what it shows that, before the treatment, the rate of deterioration was around 1.75 millimeter a month. So every month we were losing that much. So there was a movement or a tilt movement by that amount. And following the treatment, we estimate that this has gone down from 1.75 to around 0.4 millimeter a month. And this was using 2.5 tons of material. So that gave us this sort of level of degradation. And if we were to go with, let's say, a full-blown design, we would have gone for 5 tons of material, and we actually modeled what would have happened. And if we've done that, we would have managed to actually reduce that to around 0.2 millimeter a month. So it's really dependent on what the client requirement is and what sort of degradation levels that you're after. We can probably come up with a design that would provide you that design target. So that's all good and interesting. But we also had another set of data to look at, not just the tilt sensors. Tilt sensors are installed on the track, and they're great to see what's happening on the track and how the track is behaving, but they're also affected by the track skeleton response. So how the track is being anchored to the ground, and so there's an element of that data will be affected by the anchorage of the actual track skeleton. We looked at the inclinometer data. So there was an inclinometer that was installed roughly about 2-3 meters away from the actual treatment zone, so just a few meters away. And we've looked at that data to see if there's any observation that we can make out. So the tilt was installed. The inclinometer data sensors were installed right in the middle of the track, and this, if it's moved that way, it's going to be positive. If it moves that way, it'll be negative. And they had different measurements around every 6 months period. So every 6 months is roughly they've taken a set of measurements at different depths. So if we just take a snapshot of the data and try to compare similar periods. So remember, we've done the work in July, so around end of July. So I picked a period between September and February time to kind of give the track a bit of time to settle and lock in position, and then monitor it from September to February and see what happens. So before the treatment, in November 2021, the inclinometer reading was about 18 millimeters. In February, the following February, in 2022, the inclinometer reading was about 21 millimeter. That will give you a rate of deterioration of about 1 millimeter a month, roughly, if you take the delta between the two measurements and normalize them by the number of months. Okay, and this is really quantified by this gap. So this is how much movement that has been exhibited between those two periods in terms of how the core of the embankment has actually moved sideways towards the river. So that's the sort of gap. This is what it represents. Okay, now let's do the same analysis, the same approach after the treatment. Pick similar periods and do the analysis. So if we look at September, so the data we have from September 2022, so that was after the treatment. So we've done the treatment somewhere in July, so between those two dates. So if we pick September, because that's the most recent date that we can use, the reading was indicated to be 31 millimeter, and the following February was 32 millimeters. So you can see, and this is the sort of amount of movement that was exhibited within the core after the treatment, so that gap. Okay? If you take the delta of that, that gives you around 0.3 millimeter a month of movement, okay? Which translates to roughly 72% reduction in the rate of deterioration. So that's the sort of and we were getting similar sort of percentage reduction in the tilt sensor. So that is basically making sense. It's matching up nicely with what you're seeing on the tilt data with the inclinometer data. Okay. Now, one can argue and say, well, you've compared two periods, but someone can say, well, maybe you had a drier season or a drier winter last year than this year. How do we know it's basically this improvement is actually due to the injections, not due to the fact that maybe the weather has changed, the weather pattern has changed? Well, I've compared the rainfall data in those two periods in the same location. And before the treatment, within that period, between September 2021 and February 2022, the total rainfall, cumulative rainfall within that period was around 342 millimeter of rainfall. And after the treatment, I've basically taken exactly the same period. I've compared that total rainfall, cumulative rainfall, and it was actually higher. So it was slightly rainier after the treatment. So basically that tells me that water was not really a factor in terms of why we were seeing this improvement. So it wasn't because it was drier. Actually, it was actually slightly wetter than anything. Okay, so what are our findings? Our findings is that the trial has demonstrated that geopolymer injections can be used to stabilize or to reduce the rate of deterioration of slopes. So that can be used. Obviously, now, to what design specification you want to target, to what level you want to target, that's another discussion. So we can target and we are able to design to different design targets, depending on what the client wants. Also, modeling was key in understanding the overall mechanism and to also develop the treatment. The last thing we want to do is just to come in and start injecting geopolymer randomly everywhere. And I think as demonstrated nicely by Andy, it's key to understand what material you're dealing with and what's the most optimum way of dealing with that material. Okay? Now, before and after probing has shown that we've managed to improve the shear strength of the weathered clay by about 50% and the shear zone by about 340%. So we've seen that from the graphs. Long-term monitoring via the tilt monitoring, or the tilt sensors have shown that we've reduced or slowed down the deterioration by about 77%. And we've seen slightly similar values on the inclinometer monitoring data, where we showed that we've reduced the degradation by about 72%. So from our perspective, this has demonstrated that the treatment has actually worked. It did what it's supposed to be doing. Obviously, we're not saying that, the ultimate aim was not to entirely stop the movement and kill it off altogether. What we wanted to demonstrate is that actually, if you actually put geopolymer and try to understand what's going on, are you able to reduce the degradation or not? And I think the answer is yes, we can. I think that's what this data has actually shown us. Now, I'm just going to show a quick video just to give you a recap, a nice summary of what we've done on site to the people who hasn't been attended. I know some of you have actually attended the site works. I met some of you, which is brilliant. But hopefully this video should give you more insight of what happened.
So we're here today on the Severn Valley Railway. As the name suggests, the railway runs along the Severn Valley. Now, for the last 150 years since the railway was built, the water, when it rains, runs down the hill towards the river, as you'd expect. And about 6 metres down, there's what's called a slip plane. The water causes two surfaces to slide over each other. If you imagine two sheets of A4 paper, you can push them across each other. And that's been going on for the last 150 years. So for the last 150 years, civil engineers from time to time have to take some remedial action to fix the track, which is slowly sliding into the River Severn. And what we've been doing today is using geopolymers to fix the problem once and for all. So if you imagine these two sheets of paper that are sliding over each other, what we're effectively doing is applying staples between the sheets of paper. We are injecting geopolymer into the slip plane, fixing the slip plane and stopping it sliding.
The track already has some settlement sensors or tilt sensors. What these sensors do basically measure the level of tilt that the track is experiencing on a daily basis. So these sensors have been installed for almost a period of 2 years, and they've been recording data since then. And from the data, we've actually learned that the track has been losing tilt by approximately 9 mil every year. And what we're hoping that following the injections, we're going to monitor these sensors, the outcome of these sensors, and see if there's a change in the degradation level as a result of the injection. We've also done some ground probing to see the before and after results of the injections, which shown some significant improvement, and that's already been done. We tested our treatment in a virtual software or a virtual environment in the software to give us an outcome and see if the treatment is going to work. And after we kind of got good results from that and we managed to optimize the design, we've started finalizing the design and, as you can see here, installing it into the ground.
So one of the real challenges that you have with injecting geopolymers, and there are lots of companies out there that can inject geopolymers, is understanding what the problem is, what the engineering problem is, and particularly what's the engineering design solution. Because if you get it wrong, we could have built a dam here and the water's now coming down off the hill and we've just constructed a geopolymer dam. Guess what? That railway is going into that river even faster than it's ever gone in before. So the design is really, really crucial. You'll notice, if you can see behind me, and you'll notice from where the injection tubes are, the spacing is really important, the depth is really important. What we want to do is stiffen the embankment, stop the embankment from moving, but leave sufficient path for the water to continue to flow down to the river. This solution works really, really well in short intervals. If you only had 6 hours of track access, you can put the probes in, put the geopolymer in, clear everything up and be off site very, very quickly. So you can actually work in short duration possessions every midweek night, working along the track, fixing the problem so that you don't disrupt the passenger service, and that's really, really important about this solution. We can do it in short intervals, no passenger disruption, and when we've finished, you get a much better track and a much better passenger service.
So this is just a testimony that we've recently received from the managing director of SVR, and basically say that the results that they've seen on the work, following the work, are very encouraging, and they're very encouraged by that, and they were keen to work with us on this again. Okay. Now, so I think we finished the first two part of the presentation where we've introduced the material, introduced the improvement or how does it work in terms of the improvement. But obviously, stabilization or slope stabilization is not the only item that we do, or not the only type of work that we do. We do other types of work, and we decided to take this opportunity to also show you what other applications that we do on the railways. And we thought the best way to do this is to basically take you through very short case studies on the railways, just to give you an idea, a flavor of what other things that can be, geopolymer injection can be used to stabilize the track, or not stabilize, well, to treat railway assets in general. Okay, so the first example here is one of the very first railway jobs that we had is on Kentish Town slab track. So obviously Kentish Town slab track has undergone a number of renewals, or different sections had different renewals, and in my previous role in Network Rail, I used to be involved in a certain section on that, but this particular section was deteriorating I think in around 2016, and it was supposed to be renewed. So they were planning to actually take out the track and replace it with ballasted tracks, I think with some geosynthetics underneath. So that part of the track, between the time where they decided to do the renewal and until they actually do it, they wanted for us to come in and basically provide a temporary solution to stabilize the track. So the track was experiencing heavy deterioration and rapid rate of degradation in the track geometry due to the presence of soft underlying conditions and poor drainage. So that was the two main driven factors, and the slab track was basically cracking everywhere. And obviously, as some of you may know, when you're dealing with slab track, the problem with slab track is, if it goes wrong, how do you fix it? It's very difficult to restore track geometry on slab track. That's why I'm generally in favor on ballasted tracks. That's why I love ballasted tracks more, because you can always fix it and come and tamp it and get it back to the right geometry. So So what we've done, we basically carried out our injections every 1.5 meter interval, so every 1.5 meter centers, carried out almost double injections on both sides next to the rail seating area, and injected our geopolymer at 1.5 meter depth to basically strengthen the ground underneath. And the client there carried out deflection monitoring or stiffness monitoring using high-speed cameras to monitor what was the track deflection before and after the injection. So before the injections, the track deflection, as you can see here, was reaching around 6.5 mil. And following the injections, that was reduced to about just shy of 2 mil, which puts it in the ideal range of what would be the track deflection that you should have, on a normal, operational slab track. Okay. We also looked at track geometry data. So what happened in the terms of, we looked at, dynamic deflection, what happens as train passes, but also we've looked at track geometry data that was captured by the recording coach. And the red graph shows the different track geometry data at different channels, so twist faults, vertical tops, and dip angles. So track engineers here probably understand what I'm on about, but take it as there are different measures of track quality data. And this was all before the treatment, so all the red curves are before the treatment, and the dashed area is where we've actually implemented the design solution. And you can see here where there was quite bad response, even dip angles showing up. Following the treatment and the following run, this was what was the resulting track geometry. So we managed to strengthen the ground, but also almost lift it back to the right position. And you can see a significant improvement on the track geometry response after the treatment, to the point where we even eliminated the presence of dip angles. So, but that was part of a temporary solution, so it wasn't on a permanent basis. Another example of new types of work that we've been working on is to fill animal burrows. So, as some of you may know, embankments sometimes, especially if they're made of a granulous material, they tend to be more susceptible to animal burrows. So rabbits, badgers, they tend to be able to burrow through the embankment. And if it becomes excessive, it can start undermining the integrity of the embankment, and you start getting excessive settlements, which will impact the track. So this example is from Essex, where there was an 8-meter high embankment, and they had 35 badger sets there, and the sets had a depth somewhere between 0.7 to 5 meter deep, so some of them are quite deep. I've seen similar stuff on other railways, and we were required to basically install 645 kilos of geopolymer to fill those 35 sets. Okay, so we've used our injection units, mobile injection unit, and what we simply did, inserted our injection tubes in the badger sets, obviously after they removed the badgers and safely and them taken care of and spoiled and fed and all that. So we didn't kill any badgers in the process. So that's a disclaimer. So that's the sort of approach. But also to make sure that we're filling the badger sets efficiently, we also use CCTV cameras to just monitor how the polymer is spreading through the badger sets, and how it's basically forming up in the inside. Now, it's very important to understand, the dimensions of your badger sets and the spread of those badger sets, because it's very important that will impact what sort of polymer we use. So the type of polymer is crucial, because, depending on what set, you may want to use something with a very long cream time, or you may want to use something with a very short cream time, so something that goes off very quickly, or something that takes a bit of time for it to go. So it depends on the type and all that. So that is normally thrashed out during the design process. So what we've done, we basically used our mobile injection unit, and these are our injection hoses going down to the bottom of the embankment base where the badger sets were located, and we started the injections. And I've got a nice clip, it was one of my favorite clips, of the geopolymer spreading into a badger set. So that's a CCTV camera recording. As you can see here, the polymers are slowly being injected and expanding within the badger set, and as it's getting closer and closer to the camera, the operator is just pulling the camera slowly so they can see what's going on. And you can see here the polymer just starting to spread within the borrow set and expand and fill it up nicely. That was a good validation to see what is really going on inside the badger set during the injections. Okay, so that should now finish. Another example is from a level crossing located somewhere in the northern eastern part of the country. So it's a level crossing, it's a reinforced concrete level crossing where it's been suffering from significant rapid deterioration in track geometry. And this is mainly due to the presence of the usual suspect soft underlying conditions and poor drainage. And as a result of that, they ended up with a level 2 track fault, so with about 60 mil deviation from the track geometry. So from the design geometry, they were off by 60 mil as a result of the ongoing settlement. And obviously, level crossings are quite notorious for they're a hotspot, deterioration hotspot. And this is because you've got two types of traffic. So you've got the train traffic, and also you've got the vehicle or road traffic. So both of those will apply massive amount of cyclic loading into the formation, and therefore affecting you end up with a lot of settlement as a result of that. So we were called as part of emergency works to just lift the slab. So we were not required to strengthen the formation. We were only required just to lift it to the right tolerance, to the right level. So the tolerance we had to work with between 0 and -10 mil in accordance with 2102 standards. And what we've done, we basically carried out the injections 50 mil into the subbase. So we drilled through the slab at multiple locations, went 50 mil within the subbase, and injected the geopolymer. During the process, we had a number of laser level targets on the level crossing to monitor how the lifting is taking place, but we also had a third-party surveying team looking at the absolute track geometry, what is happening to the track geometry center line and each trail to avoid any sort of twist faults. And then after we finished the work, we compared and started monitoring the track quality performance run after the treatment. So the red curve represents the track geometry response in the before the treatment, and the green highlighted area is the area of the level crossing. You can see a significant response bump as you go through the level crossing. That's before the treatment. And then after the treatment, run after run, you can see that right after we finished the treatment, we managed to stop, to almost level it back and almost eliminate the harsh track geometry response. And we kept monitoring it run after run for almost a period of a year. And what we've done, we've basically looked at what's the biggest peak-to-peak value over run after run after run on both upline and downline. So we compared those two, and we were seeing similar observations. And this is what we found. So before the treatment, when they first installed the level crossing was that peak-to-peak was about 8 mil, and then grew all the way to about 34 mil, so massive deterioration. We came and intervened in around April, May time, 2021. This is where we intervened. We put back the track geometry on both upline and downline to almost new levels, the same level that I was at when it was brand new, and then kept monitoring that data for almost a period of a year. So we've taken 3 measurements after the treatment, and then we've looked at the measurement almost a year after, see what happened. And what we've realized is that it seems to have actually stabilized. So we didn't just lift the slab, we've actually managed to stabilize the deterioration. And this is because when we injected geopolymer in the subbase, we basically strengthened the subbase, compacted the subbase, created a better platform, which in turn reduced or improved the load spreading on the soft soil, and hence reduce the deterioration, the long-term deterioration. We estimate that we managed to improve the track quality and reduce rate deterioration by around 70% on average on both up and down line. Okay, and this is just detailing the values and the measurements that were taking place at different speeds and so on. Okay. Another example is from an embankment job that we've done in Poland. So what you've seen on the Severn Railway Valley this is the first time we applied this type of technology in Britain, where we stabilize embankments using this approach. But also we've done this work as well, similar type of work in Poland. Our guys in Poland have actually done some work on a railway track, which is a single line, somewhere located in the central part of Poland. And what they had was they were experiencing significant settlement due to the soft underlying conditions, but also they had animal boring. So they had 2 issues. But they didn't understand, or they didn't fully understand the extent of the animal boring as well. So they couldn't just simply insert injection tubes and fill everything. As a result, they ended up with loss of geometry, loss of shoulder, high track deflection, voiding, localized sinkholes. So the sinkholes started to appear within the track structure. We carried out an extensive injection scheme on this one. We treated about 50-meter length of the track, and we've injected at different levels, depending on where we are on the track. And we even taken the consideration of creating a transition zone to the area of treatment, because so the green dashed area, this is where the main problems were occurring. But what we had to do was create almost like a transition zone in and out the treatment zone, just to make sure that we don't create any sort of track quality faults. Okay? We've injected almost 880 injections, quite a lot of injections, to be honest with you, and the client carried out dynamic probing before and after in 2 different locations. So the red bars represents the number of blow counts before the injections, and the blue bars represents the number of blow counts after the injections in 2 locations, location 1, location 2. And you can see there's a substantial increase in the number of blow counts before and after the injections. In some instances, for example, here, almost up to 6 times in some cases. But you can see a general great improvement within the treatment area. And as far as I know from the client, the problems has basically stopped, and we managed to stabilize the problem. Another problem we've dealt with recently, actually, on Stoke Cannon level crossing. So it's a level crossing, it's a ballasted track this time, and it's a level crossing with plastic panels for the level crossing, and it's a 100 miles an hour line speed with just 10 AMGTP, so relatively low traffic. But again, that's the rail traffic, but you've got, road traffic as well, so that's driving the deterioration. And what's happened is that they've got multiple problems going on there. So they've got like a soft underlying condition, so relatively soft clay below the ballast, and obviously due to dynamic action and poor drainage, they ended up with also some subgrade erosion problems. So some of the particles of the clay started to pumping upward through the ballast, contaminating the ballast, and you can see some wet beds developing there. So quite harsh track quality, very high rate of deterioration, and we were called up to actually stabilize this as a temporary solution as well. So we've carried out, so far we've completed the downline, and we're supposed to complete the upline. So, but what we've done, we've basically injected right below the sleepers at a depth of 1.3 meter, and we extended the treatment to about 2 meters each side of the level crossing to create some sort of a transition zone, and we injected a very heavy-duty, high-density geopolymer. And one of the main objectives of the treatment, we should not create any sort of track heave or lift. So we had very rigorous monitoring there to make sure that this doesn't happen. And then we carried out pre and post dynamic probing to quantify the level of improvement in 2 locations, so on each end of the level crossing. And we've basically taken the dynamic probing data and converted it into formation modulus. So you can see here the green curve represents the formation modulus before the treatment. The red curve represents the injection, the readings after the injections. And you can see what has happened around the injection area, where we've got a substantial improvement in the formation stiffness as a result of the injections. Okay. Another example is from Ilford Rail Depot. So they had a railway depot where they wanted to increase the bearing capacity of the foundations. And what they had was about 19-foot pad foundations, 3 by 3, and 168 meter of strip foundations. And they had a combination of different clay and sandy soils, and they wanted to increase the bearing capacity to 350 kPa, so quite a substantial increase or high requirement. So we determined that we needed to treat about 5 meters below the foundations, and we managed to complete, we had to finish the work within 10 days, and we had to do pre and post plate load testing. So there was a proper testing, plate load testing involved in this. This is the testing taking place. So before the treatment, they've tested at 2 different loading levels at 252 kilonewtons and 378 kilonewtons. So before the treatment, the low loading was generating about a settlement or a deformation of around 14 millimeters. After the treatment, it went all the way down to around 4 millimeters. On the high loading, the settlement or deformation was around 34 millimeters, and that was brought down to around about 5 or 6 millimeters. So quite substantial improvement in the amount of bearing capacity or resistance to deformation. So quite a success, and probably what we've done, we've overdone it in this case, and we've overachieved the design targets. Another example where you might see a lot of social media on it, and it's quite a lot of information about it online, is the Geobear tunnel. So on that particular tunnel, we were tasked to basically fill up voids that develop behind the tunnel lining. So these voids sometimes tend to develop as a result of water ingress, and these voids were actually, believe it or not, they were about, some of them are up to 700 mil in depth behind the tunnel lining. So that's the first objective. The second objective was also to fill the tunnel shafts and seal them up and stop any water ingress as well coming from there. And this is just a photo of using an endoscope camera to actually visually examine that void behind the tunnel lining. And you can actually see some quite scary photos. And you can see, and we were required to fill that space. So what we've done on this particular scheme is we basically used a high density geopolymer, very strong geopolymer, but at the same time it wasn't it was quite light compared to what you would get from conventional grouting. And we basically drilled every meter center in a staggered pattern and basically injected the geopolymer. And what we've done to ensure that we fill everything properly, so we inject in one location and observe what will happen, how the polymer will migrate to adjacent locations, just to make sure that we fill that space and act like, and making sure that adjacent holes are acting like a release valve, so you don't build up any extra pressure behind the tunnel lining. The advantage in this approach is that you're not really adding any extra dead loading. If you, for example, wanted to use grouting in this scenario, grout has probably 10 or 20 times more the weight of the polymer that we use, so you're going to be imposing extra dead loading on the tunnel lining. And obviously, you're going to have an issue with flowability because you're going to have to create bulkheads to contain the grout. So with this approach, you tend to get rid of all this problem, and you don't need a bulkhead or any of that, and you will get almost an instantaneous solidification, and you will get almost your full strength within 6 to 8 hours in that sense. Okay, so that was the void filling from the inside, and what we've done for the tunnel shafts, we've injected a portion of it from inside the tunnel, but the second portion we've basically injected it from the outside via a geotechnical rig. So we had an inclined drilling going through the ground to the tunnel shaft and injecting the remaining part of the tunnel shaft to completely seal it. Other applications, we've got numerous examples to go through, but I'm not going to take up too much of your time. I think I've already giving quite a lot of examples, but we can, from what you've seen, we do a lot of slab track instability and geometry treatment. We also do work on transition zones, so we create transition zones in situ without taking the track out or any of that. We treat sinkholes, so if you've got a sinkhole, geopolymers are quite an ideal material to do this. If you've got foundation issues, you want to stabilize the foundation or even try to re-level it, you can do that. Void filling behind tunnel lining and shafts, you've seen a nice example. Stations, sometimes we've got a few schemes where, stations, structures within the stations are experiencing subsidence, so we treat that as well. If there's platform voiding, we can fill that. Water sealing, we can also do that. And track bed instability treatment, I think we've done that, and I think I've shown you an example. We've just finished the testing at the University of Nottingham, testing our track bed solution there, so quite an interesting results coming out. Hopefully we'll be able to share it in due course. Quite encouraging results as well. And finally, I'm just going to conclude on 2 short videos from schemes, not from the railways, slightly different, just 2 videos, and then we can conclude the presentation and go to the questions section. First video is from the M11 scheme. So on that one, we were tasked to do a void filling.
Drilling deep beneath the M11. It's midnight and this work has been taking place every night at junction 14. This a new technique to reinforce roads suffering from erosion. Rather than rebuilding it from scratch, they are injecting a special geopolymer underneath the surface that expands and then hardens in a matter of minutes.
In this job, I think we have pumped about 1,000 kilos or so, and the cavities haven't been so far as big as we had anticipated, although I have just been informed that we have found some quite sizable cavities right now, so we expect to inject more material tonight.
This Ghostbuster-style slime is afraid of no voids. It's even used to stop building subsidence. Last night they found some gaps nearly a metre deep.
All there is between the actual road pavement construction and the ground is a large air void. If a lorry or something were to park on that particular area for any length of time, there's the potential for catastrophic failure.
What, it would collapse?
It would potentially collapse, yes.
Motorists heading north on the M11 cannot currently come off the A14 heading east. They have to head to the next exit and come back round. Traditional rebuilding techniques would have used tens of thousands of tonnes of material and closed the road for months.
We are providing about 3 times faster void filling method than it would be if they would do the mass excavation that was done on the other side.
We're very pleased with this technique that we've got on this side. It's going to take us about 3 weeks. On the other side of the road where we did a more traditional technique, it took about 8 weeks, so the effect on the commuters has been reduced significantly.
Well, this work will be continuing for the next 2 weeks at night, and then this part of the road will reopen like the rest of the M11 and A14 by October the 13th. Simon Dedman, BBC Look East, the Girton Interchange.
And one final example from a sewage stabilisation solution where they had a flash flooding that affected and undermined a sewage system or a sewage junction near a pumping station. So underneath this road there was like a complex sewage system that was undermined as a result of flash flooding, and it started settling, creating all sort of cracks into the pipe works here, as you can see here from this is the BIM model, and we basically carried out a treatment and worked with the client to develop a BIM model and added our injections to it just to make sure we don't create any clashing, and we basically injected our geopolymer, large quantities of geopolymer underneath the pipes to strengthen the ground below it. It's worth noting they had super loose silt sand there, so quite a soft subgrade as a result of the washout and the erosion that resulted from the flash flooding. And on that particular scheme, we had to surgically put every injection via very accurate GPS system just to make sure that we don't hit any service, we don't hit any pipe or any of such. Quite an extensive scheme, and we had a remit to work with a certain SPT blow count that we had to achieve. So we carried out before and after SPT, where blue curve shows the SPT before the treatment, red curve was the treatment, the SPT following the treatment. So roughly about 3 times improvement in the SPT. We were having SPT's blow count of zeros almost, and some depths where we managed to actually stabilize this substantially. And I think that's the conclusion of this presentation. I hope you found it interesting and you've enjoyed it. And please, if you've got any questions, do not hesitate to ask us. Thank you all. Thank you.
Thank you very much.